In this video, I'm going to go through AS chemistry. This is AQA, the AS level paper from 2019, and this is paper 2. I'll just do the first half of this paper and the second half in a later video. Okay, so we've got 3 organic compounds, A, B, and C, and you've got to give a combination, or give a reagent or combination of reagent to distinguish them. Okay, so compounds A and B. Well, we've got one using skeletal formulae, but see, A is a ketone, okay, and B is a carboxylic acid. So the way to test for a carboxylic acid is you add some solid sodium carbonate. With reagent A, there'd be no visible change, and with reagent B, because it's a carboxylic acid, you'd get effervescence. Because carbon dioxide would be released. Okay, right, it's important to sort of not think that compound A is an aldehyde. With a skeletal formula, it's a ketone. Right, and then the next one, how would you, so the reagent is solid sodium carbonate, and there's your 3 marks there, 1 for the reagent, 1 for each observation. Same again, you've got to distinguish between compounds A and C this time, so I've just drawn the structures again. Right, A and C. Well, C is an aldehyde, so that's going to react with either phalings or toluenes. So let's do phalings. With compound A, there'll be no visible change because it's a ketone, so you can't oxidize a ketone. Phalings with an aldehyde, it will oxidize it to a carboxylic acid, so the phalings gets reduced, so you get a blue solution will go to a red precipitate. Important to get the solution and the precipitate in there. Alternatively, if you wanted to, you could use toluene's reagent, and you get no visible change with the ketone, and with the aldehyde with C, the colorless solution would form a silver mirror. So either toluenes or phalings for that second one. Right, 2. Bromoethane reacts with potassium cyanide to form D. Outline a mechanism for this reaction. Okay, so we don't actually draw the potassium ion because that's just a spectator ion. So that's a pretty common mistake. You see some people trying to draw in potassium ion. Leave that alone. You just want to have the cyanide ion, and you have a lone pair on the carbon that's going to attack. Cyanide is a nucleophile, so let me just draw. Right, we've got a delta positive on that carbon there, so it's attractive to nucleophiles. The lone pair from the cyanide, from the carbon, goes onto that carbon, and the bond between the carbon and the bromine breaks. So I draw an arrow from the middle of the bond onto the bromine to give us the product. I just draw the product like that, which is quicker, and it's now okay. Okay, so I think you probably get 1 mark for each curly arrow there, 2 mark question. Right, give the proper name for D. Okay, so this is 3 carbons long, so we call it propane nitrile. Of course, the nitrile group can only go on the end, so you don't have to call it propane 1 nitrile or anything. No numbers needed there. Right, now we've got to calculate the percentage atom economy for the formation of D in this reaction. Okay, so we've got the right, let's write the molecular weights down for each of those compounds. Right, so for bromoethane, it is for the for atom economy, we don't need to. We just need to remember atom economy. Sorry, not percentage yield. Atom economy is equal to the mass of the useful product over the total mass of the products, all the products. Well, what are we making there? We're making 1 mole of, every time we make 1 mole of the nitrile, we also make 1 mole of potassium bromide. Right? The MR of these things are, well, for the nitrile, it's 55. And for the potassium bromide, it's 119. Okay, so how much does 1 mole of nitrile weigh? We form 1 mole of it, that's 55. That's the useful product, divided by the mass of 1 mole of nitrile, all the products, and 1 mole of potassium bromide, which is 119, multiplied by 100. That gives 31.64 exactly. We should give that to 3 significant figures, 31.6, because all the atomic masses to give us the MRs, they're all to 3 sig figs. Okay, so that's the correct number of significant figures there. Right, enthalpy changes now. Okay, so a student determined the enthalpy of combustion of cyclohexane. So he got the cyclohexane above a copper can in a spirit burner here. Okay, and he had a thermometer in there. He had 50 grams of water in there, 50 centimeters cubed of water. And right, so what we've got here is they're not asking us to work out the enthalpy of combustion of cyclohexane. They give us the enthalpy of combustion, and we've got to work out the final temperature of the water. So we have to find out the temperature increase, delta T. Right, so how are we going to do that? Well, we are going to have to use the following equations. We need to know Q, the quantity of heat released in the experiment. That's equal to mc delta T. Okay, now M is the mass of the water. That's the specific heat capacity of the water. And delta T we don't know. Right. Also, we know that the enthalpy of combustion, delta HC, is equal to the quantity of heat released in the experiment divided by the number of moles of cyclohexane which has been burnt. Right. So what I'm going to do is I'm going to combine these two equations together. So I'm going to substitute the value of Q, there. So that means we're going to get delta HC is equal to Q. Sorry, not Q, we're going to get rid of that. Is equal to Q, which is equal to mc delta T, divided by the number of moles. I'm going to now rearrange that to get delta T, because we want to work out the temperature change so we can work out the final temperature. So we do that. Delta T is equal to moles of cyclohexane multiplied by delta H divided by mc. Now we need to work out the moles of cyclohexane. Okay, now how are we going to do that? Well, look, we can know the mass of cyclohexane here. So the mass of cyclohexane we're going to get by subtracting the final mass of the spirit burner from the initial mass. So the mass burnt there is 192.73 minus the other one, which gives us 0.63 grams. Okay, we burnt 0.63 grams of cyclohexane. But we need to work out the number of moles of cyclohexane, so let's do that. So moles of cyclohexane, C6H12, is equal to the mass divided by the MR. They've given us the MR. So that's 0.63 divided by 84, which will give us, this is exactly 7.5 times 10 to the minus 3. That's the number of moles of cyclohexane. Right, now we're ready to put our numbers into this equation here. So let's do that. Delta T, the number of moles, 7.5 times 10 to the minus 3, multiplied by delta H. Now, delta H is this. We're going to ignore the negative sign, so that's a heat release. So I'm going to convert that into joules, because our specific heat capacity is in joules, so we need to make sure those two sets of units are compatible. So that turn that into joules times by 1,000. So that's going to give us 1216000. Divide by the mass of the water, that was 50 grams, and the specific heat capacity 4.18 joules per Kelvin per gram. That gives us delta T a value of 43.6 degrees C. Now, our initial temperature, we need to find out what was our initial temperature. Where does it say that? It was 19.1. Okay, the initial temperature, yeah, up there, 19.1. So delta T, so temperature, final temperature, is going to be 43.6 plus 19.1, which is equal to 62.7 degrees C. That is our answer. All right. Now it says a data book value of the enthalpy combustion was minus 3,920. Okay, and the student concluded that the temperature rise recorded in the experiment was smaller than it should have been. The practical reason for that, well, they always ask this question, and it's because of not all of the heat is transferred into the water in the calorimeter. Some heat escapes into the environment. You could also say maybe there's some incomplete combustion of the cyclohexane. That will get you the mark as well, but that is the quantitatively the most important reason, because a lot of the heat escapes. So I will put that one down first. Okay, so now we have got to use a Hess's Law cycle here. So they give us standard enthalpies of combustion, delta HC data, okay? And we've got to use this to work out the enthalpy change of this reaction. Now that reaction is actually delta H formation, but doesn't really set to mention that, but it is. Now with Hess's law, you always have to have a third thing down here than your cycle, don't you? Now when you're given delta HC, the data, the third thing you have is combustion products. If you're given delta HF data, you would put down elements in the standard state, but not, we've got delta HC. So the combustion products are going to be carbon dioxide and water, and it's going to be 6 carbon dioxides and 6 waters, if you want to balance it. Do we draw our arrows up or down? Well, we're burning these things to make the combustion products, so the arrows go down. Draw that one there and that one there. Okay, let's look at the green arrow first of all. Now the green arrow, what we're doing, we're burning 6 moles of carbon. So that's going to be 6 times minus 394. And we're also burning 6 moles of hydrogen. So that's going to be 6 times minus 286. Add all that lot up together, and we get minus 4,080. Right, on the red arrow, what we're doing, we're just burning 1 mole of cyclohexane, which gives us minus 3,020 on that arrow. Okay, now we're going to find out Hess's law, use Hess's law to work out delta HC. This is the one we want to find out. So delta HC, well, what we're doing here, we're going with the green arrow. So we stick with the sign, so that's going to be minus 4080. And then we're going to go up the red arrow against the arrow, so that minus becomes a plus. So that's plus 3,920. Put the numbers in there, and we get minus 160 kilojoules per mole. Okay. And that is our answer there. Right. Let's move on to next question then. Okay, this is about fossil fuels. Crude oil contains octane, C8H18. Given equation for the complete combustion of octane. Okay, so we've got C8H18 and some oxygen. And when you have complete combustion, you turn it all into CO2 and water. Right, we've got 8 carbons on the left, so we need to put an 8 in front of our CO2s. We've got 18 hydrogens on the left, so we need to have an 18 in front of, a 9 in front of that even. Right, now let's work out the number of oxygens. The oxygens on the right, we've got 8 times 2 is 16 there, and we've got 9 here. 9 plus 16 gives us 25 oxygens. So that means we're going to need 12.5 O2s to balance it. That is the answer. Right, the combustion of petrol in car engines produces the pollutant nitrogen monoxide. Give an equation for a reaction that removes nitrogen monoxide in a catalytic converter. Right, so we've got nitrogen monoxide, which is NO. Now, in a catalytic converter, nitrogen oxides are used to oxidize toxic carbon monoxide, which is made in the engine by incomplete combustion. They oxidize that to carbon dioxide. And in the process, the nitrogen gets reduced to nitrogen gas. So that's the equation there, or gaseous. And we don't need to do any balancing there. That's all done. Okay. It's one of these mole calculation questions where they use tons and massive numbers to try and sort of get you to make a mistake. Right. Sulfur dioxide is made in the combustion of fossil fuels, and it can be removed by reacting with calcium oxide according to this equation here. Okay, in the UK, we made a total amount of that many moles of sulfur dioxide. The question is, the mass in kilograms, how much calcium oxide do we need? Okay, so what we're going to do first of all is write down the mass of sulfur dioxide. So we've got mass of SO2, it's all about interconverting the units, is equal to 6.49 million tons. So multiply by that by 1,000, and to give us there are 1,000 kilograms in 1 ton. So we're going to multiply by 1,000 to give us the mass in kilograms. That's equal to 6.49 times 10 to the 3. Sorry, times 10 to the 9, because that's a million kilograms. Now, when we work out moles, we always use grams. So I've got to convert my kilograms into grams. So I've got to times by 1,000 to convert the kilograms into grams. So that's going to be equal to 6.49 times 10 to the 12 grams. Now we've got our number of our mass in grams. We're in a position to work out the number of moles. So moles SO2 is equal to mass over mR. Right, the mass in grams is 6.49 times 10 to the 12. Divided by the mR of SO2, which is 64.1. That gives us 1.0125 times 10 to the 11 moles. Just always work in standard form, leave the numbers in your calculator. Right, now the equation shows us that 1 mole of SO2 needs 1 mole of calcium oxide. So the next little statement to write is moles of calcium oxide needed is equal to the same number. That's 1.125 times 10 to the 9 times 10 to the 11 moles. We need to work out the mass of calcium oxide in grams. So it's okay. So mass calcium oxide is equal to the moles multiplied by the MR. The moles, as we've said, is 1.0125 times 10 to the 11. The MR of calcium oxide is 56.1. That gives us 5.68 times 10 to the 12 grams. The answer, it asks us to give it in standard form, and we want the mass in kilograms. So we need to convert this grams here into kilograms. Of course, we divide by 1,000 to get it into kilograms. So that's going to be 5.68 times 10 to the 9 kilograms. That is our final answer. So there's nothing much chemistry there, but it's just being careful with your big numbers and your standard form and so on. That's all you've got to do there. Okay, methanol, CH3 is an alcohol. Draw a diagram to show how methanol molecules interact with each other through hydrogen bonding. Okay, include all partial charges and all lone pairs of electrons. Okay, so I'm going to draw a methanol here. Here's one methanol. Right, I think I'll draw this a bit of an angle because it will be an angle. Okay, and right, don't forget, oxygen always forms 2 bond pairs and it's got 2 lone pairs. So you've got 2 lone pairs there. Now it is going to you've got a partial positive on this hydrogen. That's going to be able to interact with a lone pair on another oxygen of a methanol molecule. And this is going to be delta minus on this oxygen. And this can, let's have this hydrogen. Okay, it's going to form a hydrogen bond. Should draw your hydrogen bond longer than a covalent bond because they are a lot longer because they're a lot weaker. Here's an oxygen on a neighboring methanol molecule. There's its 2 lone pairs. There is its hydrogen, that's not involved in this hydrogen bond. And here, is the carbon, the methyl group. Okay. It does ask you to draw all partial charges, so you should draw it on this methanol molecule as well. Okay, so that will get you the mark, the 3 marks. Right. The bond angle around the oxygen atom in methanol is slightly smaller than the regular tetrahedral angle of 109.5. Okay, explain why it's smaller. Right, there's the oxygen atom. You have got, if it's tetrahedral, you've got, let's say it was forming 4 bonds, which it's not. It would be like this. You've got a hydrogen there, and you've got the methyl group there, say. Right, now this is not a bond. This is a lone pair. I'll draw like that. And this is also a lone pair here. Lone pairs cause greater repulsion. So this is what you need to write down, really. Lone pairs, it's only 1 mark, cause greater repulsion than bond pairs. And that's due to the fact they're more kind of bulbous in shape. Okay, and so that reduces the bond angle. Just like in water, it's actually to about 104.5. So it's just show that you've got, I think, probably a good idea to mention you've got 2 lone pairs on the oxygen atom and that they cause greater repulsion. For 1 mark, that is more than enough, I think. Okay, now this is an equilibrium question, a long 6-mark question. So these sort of 6-mark questions, of course, you don't get 1 mark per point. It's kind of an overall impression mark you're going to get. Right, now, methanol is made by a reaction of carbon monoxide and hydrogen, and this tells us it's an exothermic reaction in the forward direction because it's a negative delta H. Okay, and also I think we need to think, this is going to ask us about Le Chatelier's principle and so on. I think we also need to point out here that we've got 3 gas moles on the right and only 1 gas mole on the left. Oh, sorry, 3 gas moles on the left and 1 on the right. So you get a reduction in the number of moles from the forward reaction. Okay, it says we're going to use a high pressure of 10 megapascals and a temperature of 550. And they use these conditions because you get a balance between equilibrium yield, the rate of reaction. Let's do this in different colors. So we've got to think about equilibrium yield and the conditions. We've got to think about the rate. And finally, we've got to think about the cost. Okay, describe how the catalyst, okay, the change in pressure and the change in temperature. Okay, we've got to relate them to the red, the equilibrium, the green, the reaction rate, and yellow, the cost. Okay, so let's leave catalyst to the last. Let's do pressure first. Okay, right. High pressure will make move the equilibrium to the right, so you get more products, which is good. And why is that? Because you've got 3 gas moles on the left and 1 on the right. Right, I should be doing that in red because it's equilibrium. Okay, so I think I'll just change the color there. My color coding has gone completely wrong. Okay, let's talk about the reaction rate in green. Well, a high pressure is good for the reaction rate. You get a fast rate of reaction. And why is that? Because the molecules are closer together. So they're more likely to collide. Finally, let's think about the cost of high pressure. Well, the higher the pressure, the higher the cost. Okay, because you need to compress the gases, you need to make the containers stronger. So high pressure, you're limited really to how high the pressure is going to go because it is costly. So you've got to balance that. Yeah, you get a good effect on equilibrium in blue, a good effect in rate in yellow, but it is costly. Right, now let's think about temperature. Now the temperature they're using here is 550 kelvins, okay? Let's think about equilibrium. 550, that's a high temperature. A high temperature, right, that is not going to be great for equilibrium because it's exothermic. So that will make the equilibrium move to the left. So you're going to get less products at equilibrium. Le Chatelier tells us that. Rate of reaction, though, and this is probably why they do use a high thing, is on the effect on the rate. So high temperature is good because you get a high temperature, you get a fast rate of reaction. And of course, cost, high temperature is costly. Right, let's think about the catalyst now. Right, so they do use a catalyst. Why is a catalyst? Does that do anything to the position of equilibrium? No effect, okay, of course, on the position of equilibrium. What does it do to the rate? So it makes the rate faster, which is good. It's going to get to equilibrium position faster. And the cost, well, it's generally speaking, it's going to save money because you can use a lower temperature to have the same effect. And most catalysts are not expensive because they're reused. They don't get used up in the reaction. So it's definitely cost effective to use a catalyst. Now, if you mentioned all of that lot, I don't see how they can't not give you 6 marks. Okay. Propene reacts with concentrated sulfuric acid to form 2 isomers E and F. Okay, so let's talk about the mechanism then. So it's propene is an alkene, and it was going to undergo electrophilic addition. Okay, so let's draw the mechanism, and we're going to form. It will ask us, I'm sure, later in this question. This is the major product, of course, and you can get a minor product it's going to probably ask us why this is the major product, but it's not asking us yet, so I won't mention it just yet. Right, so we've got here, we're going to have our propene, which I'll draw like that. It's going to react with sulfuric acid. Sulfuric acid is the electrophile because, right, here's my sulfuric acid. I'll just draw it like that, sort of not completely displayed, but partly displayed. Now this hydrogen is going to have a delta positive, with all the other hydrogen is as well, of course, because this oxygen is more electronegative. So that hydrogen is the electrophilic end of the molecule. Right, the pi bond breaks and goes onto the hydrogen there. That hydrogen is now going to form a bond to that carbon, actually, okay? And this means this bond between the hydrogen and the oxygen is going to break like that. So let's draw the intermediate there. So we're going to get that. Now the hydrogen from the sulfuric acid, I'm saying, is sticking to that carbon to give us the product they suggest, okay? And that means we have got, right, this is a carbocation, and let's just mention the fact that that is a secondary carbocation, which would be more stable if it was on than it was on the other carbon, because it would be a primary carbocation then, right? And of course we have now got our hydrogen sulfate ion like that, and we've got a negative charge on there. And the final step of the mechanism is that pair of electrons goes to the carbocation to form a bond there, and we've got our product, okay, with the hydrogen sulfate group is on the middle carbon. That's going to be our major product. Okay, I'll write that OSO3H, and we've got the H there. Okay, well, that's our mechanism there. What's the name of the mechanism? Of course, is electrophilic addition. 5 marks is a lot of marks. You don't usually get that many marks. It's usually like 4, I would have thought. But 1 mark for each of the curly arrows, 1 mark for the carbocation. I don't know where the other marks go. Right. Draw the that's E. Draw the structure of F. Right. So I'm going to just copy this picture here. This was. I'm going to copy that bit as well, actually. Right. Draw the structure of F. So I'll just put. Oops. Right. So I've got my. There's this. Right. That's the structure of F on the left. Okay. E. What I'm going to do is swap the positions of those two, the H and the other one. So E is going to be I've just copied in the picture of E there to write. So F is going to be CH3, CH2, CH2. Just draw it quickly, and we've got our O, SO3H. Or you can draw it out displayed. Actually, it's probably less. You're probably less likely to make a mistake drawing it out displayed. It's probably better safer to do that. So write it like that. Okay, explain why you get more of isomer E than F in this reaction. Right. Now, all you need to write down here is because E is formed via the secondary carbocation. F is formed via the primary carbocation. And then you need to say the secondary carbocation is more stable. I don't think you need to say why it's more stable. It is more stable, of course, because you've got 2 alkyl groups pushing charge. Sorry, I shouldn't have drawn it there. But I should have drawn the other one. You've got 2 alkyl groups. You've got that one and that one, both pushing charge into the positive charge on the carbocation. Makes it less intense. I don't think you definitely don't need to say that for 2 marks, but that's the reason why. And just to show you, if we had made E, then we would have not had the secondary carbocation, which I'll, like that, we would have had the primary carbocation, which I'll draw down here. And the primary carbocation, again, you don't need to draw this, but just for your satisfaction, I'm going to draw it. The primary carbocation would be like that. And that's less stable because you've only got one alkyl group pushing charge into this positively charged carbon atom there. All right. Now, the sort of classic mistake people make here is they say, the wrong answer. They'll say you get more of E. They say because E is more stable than F. That isn't true. It's not the products that's more stable. It's the carbocation intermediates which have different stability. So this is the sort of classic wrong answer there. So don't write that. Okay. 7. I'm going to do this one, but halfway through the paper, probably. Propane dioic acid contains 2 carboxylic acid groups. It's a solid organic solid that's soluble in water. Draw the skeletal formula of propane dioic acid. So if you're not completely familiar with skeletal formulae, I would draw it out, sketch it out normally first of all, and then turn it into a skeletal formulae. Okay, so what's that going to be? That's going to be like this. We've got 3 carbon atoms there. You've got 1, 2, 3. And on the 2 end ones, you have got carboxylic acid groups. So draw that and that. Okay. Right, so that's that. The next question. Okay, describe how to prepare 250 centimeters cubed of an aqueous standard solution of propane dioic acid containing an accurately measured mass of the acid. Okay, so this, don't forget, this acid is a solid. It's not a liquid at room temperature, so you can weigh it out. Right. So this is a fairly standard question. How do you make up a standard solution? It's one of the required practicals. Okay, so so what you would do is, first of all, you'd get let's do it in bullet points. You'd get a sample bottle containing the acid. Okay, right. You weigh it. You weigh it full. And then you transfer solid to a 150 centimeter cubed beaker. And then you weigh the sample bottle again. Of course, you do that to find the mass of acid transferred by subtraction. Okay, now you've got your acid in the 250 glass beaker here. Okay, and so that can take 250. You want to make a final volume of 250, so you don't add that much, because of course you've got to add rinsings. So what I would say is I would add, I'll put a stirrer in there as well. I'd say add approx 100 centimeters cubed of distilled water. Stir and dissolve. Okay, when you've done that, when it's dissolved, you transfer to a volumetric flask. Now, in the mark schemes, quite often you won't get 6 marks unless you specifically say it is a volumetric flask. Okay, and if you say like a beaker or a bottle or something, you won't get it. You've got to say volumetric flask, which, if you remember what one of those is, it's one of those nice shaped things like that, and it's got like a little mark. Okay, and when you make it to the mark, that's exactly 250 centimeters cubed. So you transfer to the volumetric flask. Of course, when you've done that, you're going to end up with little bits of solution all around this beaker that haven't been transferred. And so what you need to do is rinse the beaker and the stirring rod, with distilled water. and then add the rinsings to the volumetric. Then repeat that 2 times. Okay. When you've done that, then you guaranteed you've got all of the acid into the volumetric flask. Then when you've done that, you add distilled water to the volumetric up to the mark, which is there, yeah, the 250 mark, and you're done then. Not quite though. Don't forget, you then have to put a stopper in the flask and mix it by inverting it, turning it upside down several times. That's really important. If you don't, you end up with kind of like mostly just distilled water in that last bit you've added, and a more concentrated solution down there than you'd expect. Okay, so that is sort of a classic 6 mark. I've answered that quite a lot of times. Okay, so that's what you do. Right, a little calculation to finish this off. I think calculate the mass in milligrams of propane dioic acid need to prepare a 250 centimeter cubed solution. Okay, so right, we need to use how many moles, first of all, of propane dioic acid do we need? Moles of acid. Well, that's going to be the concentration multiplied by the volume. The concentration is that. The volume was 250. That's equal to 0.25 dm cubed. Of course, that needs to be in dm cubed. Standard form, that gives us 1.25 times 10 to the minus 3 moles. But it says calculate the mass, so we need to turn that moles into a mass. Okay, mass, of course, is equal to moles multiplied by the MR. The MR of the propane dioic acid is 104. So 1.25 times 10 to the minus 3 multiplied by 104, and that gives us 0.130 grams, but we need this in milligrams, so we've got to times it by 1,000, so that's equal to 130 milligrams. Okay, that is as far as I'm going to go with that paper. The next half I will do in the next video.